Hello, this is Dr. Penny Adversario, and today's session is on sampling. With the following learning objectives to be able to recognize the use and importance of sampling, to differentiate the various sampling designs, and be familiar with the advantages and disadvantages of each sampling design. Sampling is the act of studying a segment of the population to represent the whole. Most of the time, the entire population is not accessible because of financial constraints, availability of manpower, or time restrictions. The results obtained from the sample are then used to generalize about the target population. Therefore, it is important that the sample drawn must be representative of the population to avoid bias or minimize sampling errors. What are the advantages or what are the reasons why we do sampling? A study of a sample is less expensive than studying the entire population. Not only because the number of respondents is smaller, there is shorter time spent for data collection and processing. As such, you can also obtain more detailed information. And because of a manageable number of data collectors to train and supervise, you get better quality of information. For certain destructive procedures or situations wherein a study of the entire population is impossible, a study of a sample is more feasible. Example, do you need to sacrifice all animals to detect histopathologic changes from drug toxicity or extract the entire blood volume to measure cholesterol levels? We start with the definition of terms used in sampling. When we say population, we mean the entire group of individuals or items of interest in the study. It can be human, as in individual patients, or groups, as in disaster-stricken communities. It can be non-human, as healthcare facilities, charts or records, CT scans, or bioaerosols. We will focus on human populations and samples for this session. To make a useful distinction between target population and the sampling population, the population to which the investigator wishes to generalize is the target population, and the population from which the sample is actually drawn after accounting for all possible constraints is the sampling or accessible population. Ideally, both target and sampling population must be the same or nearly so, because if they differ in some important way, the selected sample may likely be biased. Example, a study on the prevalence of non-urgent visits to the emergency room. If the sampling population is from a private hospital, which caters most to HMO-accredited clientele, this would most likely result to an overestimation of the prevalence. Now, the sampling unit is the unit or units which are chosen in selecting the sample. It is made up of non-overlapping collection of elements or elementary units, while the elementary unit is the object or person on which the measurement or observation is to be made. To make this distinction, given for example a study on the prevalence of burnout among physicians in the National Capital Region, the sampling units are the government and private hospitals in NCR, and the elementary unit is the physician. The sampling frame is the collection of sampling units or list of elements in the study population. It could be a list, a phone book, a map, or an aerial photograph. Sampling error is attributed to the fact that not all units are observed, while non-sampling error is due to other factors, like measurement errors, non-response, data collectors bias, issues related to measurement and processing. In this example, a researcher wishes to determine the prevalence and profile of self-poisoning cases among adolescents in government hospitals in Quezon City. So the target population is all intentional self-poisoning cases, among adolescents seen at the government hospitals in Quezon City. The sampling population are all adolescent intentional self-poisoning cases seen in selected government hospitals in Quezon City. The sampling unit are the 5 participating government hospitals: East Avenue Medical Center, Quirino Memorial Medical Center, Quezon City General Hospital, Veterans Memorial Medical Center, and Philippine Children's Medical Center. The elementary unit is the adolescent, and the sampling frame is the list of government hospitals in Quezon City. There are 2 major types of sampling designs: probability and non-probability sampling designs. In non-probability sampling design, the probability that each member of the population gets to be selected in the sample is difficult to determine or cannot be specified. Thus, the researcher cannot assert that the sample is representative of the target population. The conclusions based on the sample cannot be generalized to the larger population. On the other hand, in probability sampling designs, each unit in the population has a known non-zero chance of being included in the sample because it specifies rules and procedures for selecting the samples. The inferences drawn are valid and generalizable to the larger population. So these are the non-probability sampling designs and the probability sampling designs. So we'll first focus on the non-probability sampling designs. In judgment or purposive sampling, selection is based on an expert's subjective judgment or some pre-specified criteria. The advantage is that the researcher can use his or her research skill and prior knowledge to choose the respondents. It is used when a limited number of individuals possess the trait of interest. In this particular study, to identify and analyze strategies used by pioneers in emergency medicine research, purposive sampling was utilized as emergency medicine researchers who have made significant contributions to research were chosen to impart their advice to aspiring researchers. Also, a qualitative study on the experiences of persons with disabilities with diabetes about diabetes self-management education. In accidental or haphazard sampling, selection is based on whatever items come at hand or whoever is available. This is typified in Vox Pop surveys where each person is asked the same questions and the aim is to get a variety of answers and opinions on any given subject. Or for example, a satisfaction survey regarding emergency room services to be given to the first 100 patients or caregivers who consult or enter the emergency room. In quota sampling, the interviewer or data collector is required to interview or collect data on a specified number of persons with a given set of characteristics. For example, a researcher wishes to conduct a study on the prescribing preferences of physicians with regards to anticoagulants. If the list of physicians in an institution show that there are 60% cardiologists and 40% critical care specialists, and the researcher wants a sample reflective of these proportions, once a quota is set, quota sampling merely consists of finding persons with these requisite characteristics. Therefore, from a sample size requirement of 200, the data collectors are given specific instructions to keep on interviewing cardiologists until 120 is reached and critical care specialists until 80 is reached, because 60% of 200 is 120 and 40% of 200 is 80. This is the non-probability equivalent of stratified sampling. While in convenience sampling, study units that are easily accessible get to be selected as samples in terms of proximity to one's residence or workplace. Sometimes this is referred to as accidental samples for the reason that elements may be drawn into the sample because they happen to be situated spatially or administratively near to where the researcher is conducting the data collection. In actual clinical studies, patients are not always randomly selected from a population. The clinical researcher often uses all patients at hand who meet the entry criteria for the study. Other ways are recruiting friends to participate in your study, like resident friends in training from other schools, collecting data from locations that are nearby, sending a survey in the mail, or sharing a link on social media. This is an example of quota and convenience sampling. In this particular study, convenience sampling because the participants were recruited from a community-based organization helping PLHIV. Snowball technique involves study of hidden populations like drug users, commercial sex workers, some LGBTQ plus community, or other inaccessible groups. This is devised because of the difficulty of producing a sampling frame and identifying members of this population. It stems from the analogy of a snowball, which begins small but becomes bigger and bigger as it rolls downhill. That is why the first person identified to be a member of the target population will be interviewed for the study and will be asked to identify other members of the population. In this particular study, there was difficulty in accessing the study population due to the illegality of crack cocaine use. Other examples of hidden populations for which this technique can be useful are battered wife or child cases seen at the emergency room, or sexual abuse cases referred to the Child Protection Unit. The advantage of non-probability sampling designs is that they are easy to execute, they are less costly, and for certain studies where it is the only possible means, like snowball sampling. On the other hand, it may compromise the validity, reliability, and generalizability of the results. We now go to probability sampling designs. In simple random sampling, units are selected independently, one at a time, until the desired sample size is reached. It is used in small populations with readily available sampling frames, or for populations that are homogeneous with respect to the characteristics that we are interested in. For example, a profile of males who have undergone non-scalpel vasectomy, or burned out among faculty from the basic sciences. In simple random sampling, it starts by listing all the elementary units of the population. Then the required number is selected randomly using a table of random numbers or the rand between function in Excel or a software. This is a table of random numbers. So how do you use a table of random numbers? From a community of 80 households, a sample of 10 households is desired. So from a random start, which is obtained by letting a pencil drop at any point on the table, a two-digit number is taken consecutively, either horizontally or vertically, until you get 10 households. For example, the pencil landed on 44249, second row, second column. First pair is 44. This refers to the household number. So the sample contains household 44 followed by household number 24. The next is 90, but this is dropped because it is over and above 80 households. You now proceed to get the next eligible pair, which is household number 40, until you reach and get 10 households. This is using the run between function in Excel and a software such as Randomizer. The advantage of simple random sampling is that it involves a simple design and analysis, but requires a complete listing of all the elements in the population. It may not be feasible for units that are widely spread and heterogeneous with respect to the variable under study. In this example, the sample of diabetic patients with diabetic foot ulcer is a homogeneous sample. In systematic random sampling, the samples are chosen at regular intervals. Even when a sampling frame is not available, systematic random sampling may often be applied. It starts by determining the sampling interval, which is denoted by the letter K, and computed by dividing the total number of the population with the sample size. A number is drawn randomly between 1 to k. Then each kth consecutive unit is chosen until the required number is reached. For example, from a population of 500 charts to be reviewed, the sample needed is 100. So 500 divided by 100 is 5, which is the sampling interval. A randomly chosen number between 1 to 5 is 4. So from 4 plus 5 is equal to 9. The ninth chart will be chosen. Then 9 plus 5 is equal to 14. The 14th chart will be chosen. Then 14 plus 5 is equal to 19. Then the 19th chart will be chosen. Then so on and so on until you get 100 charts to review. Therefore, the sampling frame is compiled as the study progresses. The advantage of systematic random sampling is that it is easy to perform even when no sampling frame is available. Unlike simple random sampling, systematic random sampling requires the selection of only a single random number. It distributes the sample evenly over the entire population, only when the sampling units are not widely spread out. Bias may arise if there is some type of periodic or cyclic sequence in the list. For example, selecting months of the year in a study of the different types of accidents, because some accidents occur more often at certain times of the year. Or if a researcher wishes to investigate completeness of medical records at the emergency room, and it involves auditing more than 1,000 medical records of patients, one can randomly select by doing systematic random sampling of the ER charts. This is an example on the use of systematic random sampling in choosing households for a diabetes survey. When is stratified random sampling used? In cases wherein the population is heterogeneous or varied or diverse with respect to the characteristic under study, that is, for example, a mix of males and females or different age groups, and when you think such characteristic may have an effect on what you are interested in, the population should first be divided or stratified into more or less homogeneous subpopulations or strata of age or gender before sampling is done. Commonly used strata or stratifying variables are age, gender, religion, educational attainment, socioeconomic status, nationality, or disease severity. The difference with simple random sampling is that simple random sampling does not take into account or take into consideration any information that is known about the elements of a population that might affect the characteristic of interest. It is possible that a particular subgroup of the population might not be represented in a given sample purely by chance. For example, in selecting adolescent cases of poisoning, we might not be able to choose the early adolescent age groups. We can avoid this problem by doing stratification. This method ensures that each stratum is represented in the overall sample, and this will more likely lead to reliable results than a simple random sample of the same size. The number of samples allocated for each stratum is proportional to the stratum's distribution in the population. Since simple random sampling is done per stratum, a listing per stratum is needed. You cannot use this unless there is some information concerning the population. In this study on the effect of COVID-19 stay-at-home orders on the rate of foreign body ingestions, the patients were stratified into age groups as less than 5, 5 to 12, and 13 to 18. The number of samples that fall into each stratum is not determined equally, but proportionately depending on the stratum's contribution to the population. Suppose we want to allocate 250 samples to 3 sample barangays included in the study. These 3 barangays have the following population: 3,000 for Barangay A, 10,500 for Barangay B, and 6,500 for Barangay C. In the third column, Barangay A comprises 15% of the total population from barangays A, B, and C, which is derived by dividing 3,000 by 20,000. In Barangay B, 10,500 divided by 20,000 is 52.5%, and in Barangay C, 32.5% results from dividing 6,500 by 20,000. So from a computed sample size of 250, we distribute the number of samples proportional to each barangay's contribution to the population, such that if Barangay A constitutes 15% of the population, 15% of 250, which is 38, is the allotted size for Barangay A. The same is true for Barangay B, which is 52.5% of 250 is 131, and 32.5% of Barangay C is 81. This sums up to 250 samples. Cluster sampling is resorted to when the sampling frame for the elementary units or elements are not readily available or when cost considerations are important, as in a study on disaster preparedness of communities along a fault line. In this design, the sampling units are the clusters of elements. The clusters are commonly based on geographic areas or districts. The procedure first involves dividing the population into clusters, then selecting a random sample of clusters. If all elementary units within the chosen cluster is selected, then it is a single-stage cluster sampling design. If only a subset is included, then it constitutes a multi-stage sampling design. In the adolescent poisoning study, the hospitals are the clusters themselves. It is usually more economical than other types of sampling. It saves both time and money. However, because of the tendency of the elements within a cluster to have the same characteristic, the rate of homogeneity or similarity is high within a cluster, and the amount of information provided will be less. This can be addressed by increasing the sample size requirement for clusters. In this example, the 18 medical wards are the clusters. In summary, we have an illustration of the 4 sampling designs: simple random, systematic random, stratified random, and cluster sampling. Multi-stage sampling designs are used in community-based studies or nationwide surveys. It is carried out in stages involving more than one sampling method. From the first stage, primary sampling units, a sample is selected. From the selected primary sampling units, secondary sampling units are selected until the desired stage is reached. In multi-stage, a complete frame is necessary only for the primary sampling units, while the frames for the secondary and succeeding stages of the selection are only confined to those selected as samples. As an example, a nationwide study was done to determine the prevalence of drug abuse among teenagers in the Philippines. So from a total of 16 regions in the country, 6 regions were selected. This is the first stage. Then from the selected regions, 2 provinces were selected, resulting to a total of 12 provinces. This is the second stage. Then from each province, 4 high schools were selected, totaling to 48 high schools. Then from each selected high school, 50 students were selected randomly. How many stages do we have? So the sampling design is a 4-stage stratified random sampling design. Very seldom are sampling designs used in their pure form. More often than not, a combination of designs is utilized. So this is the 2001 Behavioral Risk Factor Surveillance Survey. It's a cross-sectional study conducted among Filipino adults aged 15 and above to establish baseline data for risk factor surveillance. From the 16 regions in the country, 2 provinces were selected. From each of the 2 provinces, 2 municipalities were selected, and from each municipality, 2 barangays were selected. Only 1 adult member was interviewed at random from each of the 8 households in clusters in the chosen barangay. The sample included 640 respondents per region, or 10,240 respondents in the 16 regions. Can you identify the sampling design? Obviously, this is multi-stage. You have a combination of designs here. One is stratified, another is cluster, and one is your simple random sampling. So this is a 5-stage stratified cluster simple random sampling design. This is another example of multi-stage sampling using a combination of designs. Out of 100 primary sampling units, there was stratification into urban and rural. Households were selected using systematic random sampling. Then from the selected households, which were the clusters, 1 household member aged 18 to 69 was selected using the Kish method. This method makes use of pre-assigned table of random numbers to find the person to be interviewed. So these are my references, and thank you for listening.